remember like what breadth first search is. So the idea is, it's comprehensive, just like DFS is, and we're going to visit these nodes in levels, right? So first we'll visit A, then we'll visit B and C, and then from there we'll visit D, okay? And the way that we implement it is we use a queue, meaning that the first node that we visit, that's the first node that we'll like process. And by process, or like first in, first out, right? So in the order that we visit the nodes, that's the order that we'll process the nodes. So if we visit node A first, when we process it, that means this will be the first node that we print, and that will then add A's children next, right? Then we'll add B and C, and in that order, we'll then print B, add B's children, print C, add C's children to the queue, and then finally process this node D. All right. So let's do that. So the first thing we'll do is initialize a queue, right? And we use this dec function because this is like that doubly ended queue, right? And the idea is we're gonna have to like do a pop left, right? We're gonna have to remove from the front of the queue in order to make sure the first thing, like if A is in the front of the line, it gets processed first. And then the next thing we'll do is something like, okay, while there is a queue, we'll do the current node, and I want the first node, just to initialize this, it should be the root node, right? So this will be A will be first. And then we'll do, okay, while there's a queue, we'll do, so we'll do queue.popLeft, and this will be my current node, okay? And then what we'll do is visit, basically print the node, like process it, is the way I think of it. So we will, and that's getting actually annoying. So we will print the current node, and then we're going to visit this current node's children. Okay, so we'll say for child in tree of, and we like to do the tree.get the current node, and do an empty list. So what this will do is basically say, okay, tree.get, the current node is an A, right? The get A will give us back B and C. And we do this empty list because if it's not there, like say we try to access D, tree.get of D, it will just give us back an empty list and then effectively do nothing, right? Iterate through an empty list, which will do nothing. So, okay, so for each one, then what do? We'll add to the queue. Queue.append the child. I think that is there's one more like kind of twist we can do, but for just getting this done, I think that's essentially it. Let's try it. We can print out some stuff. So let's print the current node, the queue. I think that's probably pretty good. All right. So we'll do BFS root and the tree. And I broke something. Local variable current node reference before assignment. So what we want to do is pop this, and then we can print it, right? So I just had this line before I actually removed and assigned my current node. Okay, so let's think about it. So we have the current node is A, right? We removed it, I guess, from the queue. Then next would come, it might actually be a little easier. I'll just move this line up. Okay, so we can see the current node. So we start with a queue of A, right? That's our root node. Then we remove it, that the current node is A. Then we process it, right? So we'll print this current node, and we'll add the children. So now you can see that in the queue, we have B and C, because we went through each of the children, added in each child there, so we got a queue of B and C, and we're always removing from the left, right? This way, this is what kind of like makes it breadth first search, is that we're going in order. And you can see that, so then we process B. B does not have any children, so we're good. Then we move on to C. C does have a child, so we add in D to the queue. And then finally, we process D, and we're done, right? Because now my queue is empty. The only other thing that you really can add, or you can think about adding, right, which is a good idea, is to do this visited thing, right, which is just to make sure you don't revisit certain nodes in case there's any cycles or anything like that. And so how do we do that? We basically keep a list of visited, and we say we get this current node, and then we basically say if current node not in visited, right, then we'll process it and add the children, right? Basically, if we haven't seen, if we hit this node, we want to make sure we haven't seen it before. So we put this in here, and then the only other thing we need to do is add, let's just add visited dot add the current node, all right, to the list of visited nodes. Okay, so the same exact thing occurs, right? We initialize with the root, we process A. When we process A, we also add the children, B and C. Then we go always the first in line, right, gets processed because we're doing that pop left. All right, so then B gets processed, and B has no children, so we're good. Then we process C. C does have a child, so we add in D, right? And then once D is processed, we're done. Any questions about that? Or anything to review with that? Okay, so the next thing is here's the next challenge is, can we add levels to this? By that, what I mean is, instead of just printing out A, if we say we even, just for debugging, we don't have this. See, we're here, we're just printing them out in order, A, B, C, D, right? What if we printed out A is at level 1, B and C are both at level 2, and then D is at level 3. Okay? So how do we do something like that? The way there's two different ways we can do this. The first way is, instead of initializing a queue with just the node, right, with just the letter A, we'll also store here the level. Okay? So we'll say this is an A node, right, at level 1. And this is our queue. So our queue is going to have that. And let's go back to printing this out so you can see what's going on here. And now the next thing we'll do is, okay, while there's a queue, we will remove that node from the left, so this A thing. We'll visit each of the, if the current node is not in visited, fine. We'll process the node, add it, print it, add it to say that it's been visited. And then we're going to append not only the child, but we'll also, remember this queue should not only have the child, the letter A has children of B and C, so not just B and C, but also their level. So how do we get their level? The way that we can do this is, when we do a pop here, pop left, remember this is going to have a tuple here. So we can actually unpack this as current node, comma, level. Right? And let's call this current level. So in other words, this is, I can kind of show you this. So initially this would be current node of A, and then level is going to be 1, right? And then when we add the children, we can add not just the child, right? So that would be B and C, but also the level is going to equal current level plus 1, right? Because if we're visiting one of the children's level is just going to be 1 more, right, than that parent's, right? So we're processing A. A is basically the parent. Then we get to the children, and the children's level is going to be, both B and C are both going to be 2, right? 1 plus A's level. Then we'll get to B, and then B has no children. We're good with it. C does have children. C's current level is going to be that 2. And so when we add in D here, we're going to just do current level plus 1, and that will be 3. Let's see this. And I broke it because I need, Oh, I'm missing an end parentheses here. Line here, q dot append right here. I'm missing an end parentheses. And what else am I missing? Name level is not defined. It should be current level. Okay. So you can see we initialize with a tuple, right? Both the letter and the level. Current node is A, level is 1. And then we do Q. So when we add in B and C, we're adding in, right? We get the current level, and we add in not only the child, but the current level plus 1. Okay? Then let's say we pop off things. We pop off B. That gives me level 2. There is no B, B children to process, so we're kind of done there. Then we handle C. That has a level of 2. So we do current node, comma, current level. That gives me C and 2. And then we say, okay, let's go through the children of C, which is this guy, and we say, what is the current level, or what is this guy's level? It's just the current level plus 1, right? So it's C is at level 2. That means D's level is going to be C's level plus 1, right? So we're getting that by kind of storing it within, storing it in the queue. Does this make sense? Any questions about this?
Hey Jeff, what was the use of visited? Again, sorry, I forgot.
What's the use of, visited?
Yeah.
It's just like if, let's say this thing has a loop, like let's say it goes to E, and then E points to D, right? Now you have a cycle, basically, right? And so you can re-hit, right? Or it's possible to like see a node twice, effectively.
In that case, shouldn't we check while we are appending to the queue that if it's already visited, we don't need to append to the queue?
Well, this is happening right here. If the current node is not visited, yeah, then we say that we've seen it. Then only do we say we've seen it. We basically process it by printing it, say we've seen it, and then add the children. Only if we've never seen it before. Okay, so this is one way that you can handle this, right? Is storing the level along with the queue. The other way that you can do this is very similar. Is you can have basically a separate dictionary. Okay, so we can kind of do this. Instead of this visits things, we'll call this distance. It doesn't really matter. We could call it level as well, but I'll just call it distance because you'll see that word sometimes. And then we'll say, okay, distance is an empty dictionary, and we'll say the distance is, we can do the same thing. Level for node, we'll say for node A. Let me move back these, just so you can see this data. We'll say for the root node, it's going to have a distance of, you can say 1, sometimes you'll say 0, right? But whatever you're calling that first level, 1 or 0, right? We're going to say, put that here. And then in the queue, we're back to just placing the root node, all right? So instead of storing the level here, we're storing it down here, okay? And this root is going to start off as an A, and then this is just a dictionary, right? So right now it's like A has a level of 1. Now what will we do? So while we have a queue, this is just for debugging, right? Print the queue. Then we will, here we're not unpacking because there's just one, we're just storing the node here. So it's just current node is queue.popLeft. If the current node is not in visited, we can call this distance. We'll see this is the same. You can use an in for, if you use in on a dictionary, it's just going to look at the keys. Is this key in the keys in the dictionary? So basically, if we haven't seen A before, process it. And now we can print the current node. That's this current node from right here. What's the current level? How do we get that? And that's going to be, for current level, we can say current level equals what? Well, it's going to be distance, square bracket, the current node. Right? Because distance, current node of A will give me back 1. Right? and that's the level. And then everything else is the same. Current level is going to be 1. We say we've seen it before. Go through the list of children. And then we're going to add current level plus 1. So the only difference here is that instead of getting the current level from the tuple, we're getting it from this dictionary. And the other thing we should do actually is not add to the tuple, not add the tuple to the queue, but rather we can do this. We'll do the distance, we'll update our dictionary, of the child equals the current level plus 1. Okay? So I'll just print this stuff out so you can see what's going on. So print out the queue, print out the distance thing too. Oh wait, we did not go through everything, did we? I wonder if current node not in distance, q dot append child. Okay, so distance q equals root. Current node is q dot pop left. Here's my, I need to add it. If current node not in distance. Oh, I think it's because of this. Because the current node is in distance. Shoot. So how would you do this? Current level. That's fine. Yeah, I guess we would. I think I'd have to. Let me take out this if block for now. I mean, you could start it at 0, and we could just do it right. Yeah, I don't know. I'm going to take out this if block for now. Sorry, I'm not quite sure. Okay, so all I did was, remember, we only had that like if block to make sure we don't revisit a cycle. Just for debugging right now, to make it a little easier, we'll just remove that if block. So here's the queue, here's the distance. The distance is this dictionary that has A points to 1. Current node is A, level is 1, right? Then we go through each of the children. We're going to add them to the queue, right? Add them to this queue. So notice we're just adding, we're not adding a tuple this time, and we're adding a distance, right? We're adding the distance here of, B, the distance is 2, C, the distance is also 2. Okay? Then when we say then we get to the next one, right? Go to the queue. The next guy in the queue is B. B doesn't have any children, so we basically just print it. Then we go to the next guy in the queue, that's C. Okay? And we say we process it. Here's the queue, the distance, we process it. Here's the current node is C. Go through the children, right, which is D. And then in calculating what is like the distance here, it's D's, right? It's the distance in distance in C, which is level 2, right? We've stored that. So we just get that distance, and then we add 1 to it. And we store that as well. So this is the same exact approach. The only difference is that we're not storing the distance, like this kind of level thing, in a tuple in the queue. We're rather just like maintaining a dictionary throughout here. All right. Now let's see if we can do this coin change problem. So this is what's kind of tricky, I think, is like, all right, like and this is what I wanted to like bring you towards is, okay, how does this coin change problem relate to like breadth first search? Because this is, like I said, this is a super popular problem that we see. So I want you to get the real way of approaching something like this, right? To like solve this fully. Because if we just do the greedy approach, remember like what we learned previously was the greedy approach, and that actually won't work. Because let's say we have an amount of 6, and we say, okay, let's just remove, start with the largest coin and remove as much as possible and then try to keep subtracting the remainder. So if we minus 4 here, that will give us 2. And then we try to find a number, right, like a value that we can subtract. We're done. We can't, there's no way to get to an amount of 6 once we remove the 4, right? But there is an answer here. It's to use 2 3s, or you can use like 6 1s, I guess, right? But the real right answer is to use 2 3s. So how do we do this? Well, the way that you can do that is you can think of like all possible, the tree as representing like all possible amounts, okay? So here we're starting with an amount of 0, and then you can go through the different coins, right? We can either add 1, 3, or 4, all right? Then for this, say we choose coin number 1, right? So we have denominations of 1, 3, or 4. Our target equals 6. So let's say we choose a coin of 1. Then we can add 1, right? 1 plus 1 give us 2 to our next value. Or we can add 1 plus 3, right? Give us 4. Or we can add 1 plus 4, right? Give us 5. So when we get to 2 coins, this is, and we choose a 1 the first time, this is the next set of values we can get, is 2, 4, and 5. If we choose 3, then the set of values we can get is 4, 6, and 7, right? Because it's 3 plus 1, 3 plus 3, 3 plus 4. We've solved the problem right here, right? We're trying to get to a target of 6. So the problem's really done at this point. But we'll just keep going, right? Say we chose a 4. Then it would be 4 plus 1 is 5, 4 plus 3 is 8, 4 plus, and this should be 4 plus 3 is 7, my math is bad, and then 4 plus 4 is 8. All right, so you can kind of see, like, you can start to see how we can use breadth first search to do this. All right, so I'll show you what this looks like in code, I hope. So here we go. So the first thing is, this is my amount, right? The Q is basically representing my amount, or like, which is the root node, which is 0, okay? And then the distance of this amount is 0, like it takes 0 steps, like 0 coins, right, to get an amount of 0. So then what's next? We'll have while Q. Okay, so while there's a Q, we're going to Q dot pop left. This is my current value, or current amount. And then we can basically say for coin in coins. So we're basically going to iterate through each one of these coins, right? 1, 3, and 4, and we're going to kind of get the next amount, okay? Where the next amount is the current amount plus the coin. Okay, so let's say we do 0 plus 1. All right. The next thing is if this next amount is less than, right, like the target amount, right, the amount that we want to reach, then we let me actually do the base case next. If it equals it, if the next amount equals the target amount, then we're done, right? Then we return the current level. Like, basically, we're done, and we can return the current level. And we can kind of say what that is. So the current level is going to be the distance of the current amount, right? So it'll be distance of current amount. That's going to equal the current level. Okay? So basically what we're doing is we have this Q, right? So we start with 0. We're going to go through, we're going to get the current amount. What are we on now? So we're on 0, right? The current level is going to be 0, right? We've not gone anywhere, but we're just kind of storing that here. And so we go through each one of these coins, 1, 3, and 4. Let's just start with 1. Start with 1. We've calculated the next amount. That's 0, current amount, plus 1. If the next amount equals the target, we are done. Okay? Return the current level. else, we can do something like this. This is what normally how it's coded out. If the next amount is at least less, sorry, if the coin, yeah, if the coin is less than, I think it's this, less than the target amount, right? In other words, if if we can't use a coin that's larger than our target, right? Like if we have a coin of 10 and we're only trying to hit 6, we're not going to use it. So let's say if the coin is less than the target amount, then we need to add this to the queue. So let's think about this. We take our next amount and do the queue dot append the next amount. We're going to add it to the queue, right? So it'll be like this 1, right, that we're going to add to the queue of needing to like process next, of kind of like what is like, these are the different options, right? 1, 3, and 4. We're still not going to hit our target. So next we're going to need to like iterate through these coins again. So this is saying, okay, if the coin is less than the target amount, add it to the queue. And we also probably need to say what is the level, like what is the corresponding level here. So what's the corresponding level? It's going to be the current level, right? So current, the distance of the current of the next amount equals the current level, right, which comes from here, plus 1. I think that's it, actually. So let's think about this. By the way, everything here is just like the algorithm we saw before. The only difference is an if-else statement. That's really the only difference. So these two things are really exactly the same. We're keeping track of a distance each time and incrementing that distance. The only difference is in this case we're saying, okay, the next amount equals, this current amount plus the coin, so it's 0 plus 1. And then if the next amount equals the target, we're basically good. We're done. Return that this should be current level plus 1, probably, because we've hit this, let's say we've hit this level. And then otherwise, we're going to add these, keep going and basically add this coin to the queue. If the coin is less than the target amount, queue.append coin number 1, add in the target, add in this level. So the level of Q1 of 1 is going to equal the current level plus 1. So that will give us something like this. One colon 1. Then we'll go to 3, right? That will do the same thing. And then we'll go to 4. That will do the same basic thing, right? So 1, 3, and 4 will all be at level 1. Then think about what my queue is going to look like. We're still going to have to process. We're going to have to pop left. So I'll remove 1. And then we're going to iterate through all the coins again. 2, 4, and 5. Right? For coin and coins, calculate the next amount. So that'll be 1 plus 1 is 2. And then we're going to say, okay, if 2 equals my target, if we hit it, we're basically done. Right? If not, then we need to append in the next amount, this 2, and store also like the current level that we're at, right? So the current level of 2 is going to be, 1 plus 1, right? So leading to 2. Let's start printing this out. I'm pretty sure this is right. Let's start printing out some of the statements so you can see how this works. So I'm going to do, do print the queue, print the current amount, and print the current level. And then if you want, I think we're probably, let's see what happens. Yeah, so let's see this down here.
Yeah, Kamal said something in the chat that I was also thinking. The second if statement is just coin less than target amount. I think you mean coin plus next amount because you're going to the
Coin plus the next amount.
I mean plus current amount, I guess.
Yeah,
Or if next amount is less than target amount.
I was thinking of that too. We could try that. I mean, it's basically, yeah, making sure you don't exceed that target. Yeah, we could do that. I think either way it's gonna be fine. Let's see. Current amount is not defined. Q.pop left. Current. Oh, I misspelled that here. Let's just do that. Wow, Q. This should be a second R here. I think we're good otherwise. Current amount, 2 R's. Okay, so that didn't break. Current amount is not defined. I misspelled it here too. Line 15. Here's 2 R's. Let's see if there's any more. That looks okay. Okay, so that did work. Let's show it again, because I know this is a little tricky. So we start with our Q. Our Q just start with a 0. We're basically moving through this tree. So we start with a Q, it has 0. We remove our current node, so that's this 0, right? Current amount is 0, current level is 0. Then we're adding in, so the whole difference here is that instead of adding in the children, instead of adding in, the children of a node, we just iterate through all the coins. And kind of those are the children, 1, 3, and 4. The only reason why you don't see a 1 here is because we already moved it. So we add in 1, 3, and 4, then we pop left, remove the 1, right? So now the current amount is 1. And also notice this current level is also 1 because of this distance thing, right? This distance has already been updated. It gets updated when we do distance of the next amount, right, equals the current level plus 1. So let's just, so you can see how that works. Then when we get to, so our Q is 3 and 4, we've processed the 1. The next thing is we're processing the 3 next, and we're adding in 3, 4, 2, 4, and 5. The only one I'm confused about is this 2, 4, and 5. Yeah, I may just have confused myself here. Let me print out the Q before we. Hold on, where do we print the Q? Oh, here's the Q getting printed. I just want to print this out. It'll make it a little easier. So the Q starts at 0. Then we add in 1, 3, and 4. Right? Those are the 3 coins. We process the 1. Right? The level gets incremented, so that's the 1. Remove it from the front here. Then we have the 3 and the 4 are left. And then we add in, yes, this is correct, right? Because we add in, 1 plus 1 is 2, 1 plus 3 is 4, 1 plus 4 is 5. And then we process these as well. The only thing that would be beneficial for this is that if we had an if check again, if we basically said, hey, if we've already seen this amount, don't process it again, okay? But otherwise, this is correct, right? And it does get us to the right answer, which is that you basically need 2 coins, right? 2 3s to calculate this. So this is a valid solution. This will pass your interview, and it uses breadth first search. Again, the only difference here, there's really only 2 different. I know it's confusing, but there's only really 2 differences between what we saw before. The first difference is that instead of iterating through the children, we're iterating through each one of the coins. So we kind of have a current amount, that's like the current node that we're on, right? And then we iterate through each one of the coins to figure out basically what can possibly come next, right? and we add in, right? We go through each one of those coins, add in a next amount, and add that next amount to the queue, as well as that next amount's level as the current level plus 1. Okay? I'm trying to think if there's any other differences. That's basically the only difference between what we saw previously, right? Remove from the queue, current level. Here we go through all the children, add them in, right? Add them to the queue, distance of the children plus 1. Here, we just go through each of the coins and then calculate that next amount, and those next amounts become the nodes that we add in to the queue, right? And then the only other difference is if we hit the target, exit, return the current level, and you're done. Okay? So the reading has you go through these steps of first breadth first search, then breadth first search with levels, finally breadth first search with the coin problem. This isn't the only problem where you kind of can use breadth first search, and basically have to use breadth first search to solve it. So that's why we're going. This isn't just like to challenge you. Like, I wanted to go through this because it's a way to review, and it's a really useful application that will help you solve some of these leak codes. So do spend some time going through this, even if you only get to the levels part, right? Like, that will still be beneficial to you. Other questions about this? Do you start to see how this translates to a tree, and you're basically just moving through, right, all the possible, right? The reason why breadth first search is successful here is because it's a way to move through all possible combinations, right? This is all possible combinations when you have one coin. These are all possible combinations when you're using 2 coins, right? And that's that's why breadth first search works. It's because it's an exhaustive way to visit all of the paths.
If I wanted to understand, because I'm still not clear, I understand the algorithm to a great extent. I'm still not able to follow what is guaranteeing here. I know the answer is right, but I'm not sure what is guaranteeing here. It's always giving the minimum number of coins there are. That's what I'm not able to follow here.
What is giving minimum, what?
So the coin change problem is essentially the minimum number of coins required, right?
Yes.
So what is exactly guaranteeing that here in this algorithm is what I'm trying to understand.
What is getting what in the algorithm?
So how this algorithm, which part of this algorithm is guaranteeing that this will be minimum coins? The answer will be essentially minimum number of coins required for getting that particular target amount.
The minimum, so because it's calculating the level, right? If it's here, right, it's 0 coins. I'm sorry. But once it gets to this level, right, how many coins are required? 1 coin. So if it finds it, at this level, once it hits this part, you're keeping track of the level, so the level is 2, right? I think that's I'm not totally following your question, but so this is so basically this is going to be once you get this, we're going to have the current amount, let's say, is 3, and then you get that current amount plus 4, we try it, plus 6, plus 1, plus 3, plus 4, each of my coins. Once we hit the 6, then we're basically exiting the program, and we get that current level from here of this guy plus 1, right? And that's what we end up returning. Was that your question? Kind of?
Yeah, I'll actually do it on through my sources, so thank you.
Yeah.
No, that's fine. I was just going to try to restate. He was asking, how do we know for sure that it's always the fewest number of coins possible?
Oh, I see. Good question. Yeah, because breadth first search by definition processes level by level, right? So even if, I think maybe what you're wondering is, what if there's an answer over here? Like what if it's like this combination, 4 and 2. Let's say there was like a 2, and that equaled 6. It doesn't really matter because either way, whether you do a 3 and a 3 or a 4 and a 2, you're still using 2 coins, right? So because it in this level here, this represents 0 coins. This represents 1 coin. This represents 2 coins. So because with breadth first search you're moving through level by level, you're never going to hit it. You're never going to move through the option of 3 coins before you exhaust all of the 2 coin combinations.
How would this example scenarios if we are only able to attain a value, for example 10, and I know 10 can be formed using different combinations, but assume 10 was to be formed using 2 fours and then 2 ones.
Yeah, so it would be 4 here, then it would be this 8, right? And then you would go to this level, and you would see, you would go through all the options with 8, right? So 8, you would go through all the 3 coins. Does that make sense? So if it could be solved,
that's more coins than is optimal, right? To get to 10, you would say 4, 3, 3.
4, 3, 3. Well, you'd hit
it would
it
actually
right here.
branch off of 7.
Well, you'd hit it here, yeah. I mean, either way, yeah.
You'll always get, because it will exit the first time the sum is reached.
Right.
You'll always guarantee that it's the fewest number of coins.
Exactly, because you're always gonna process every node at this, at the lower level before you get to a subsequent level. So what I'm saying is it is exhaustive basically. Like that's the whole trick, is that you are looking at every combination using 0 coins, then you're looking at every combination using 1 coin, seeing if it hits the target, then you're looking at every combination using 2 coins. Then you're only right, and then you're looking at every combination using 3 coins. Does that make sense? So there's no way that you can, right? If you hit it when you're doing 2 coins, you're not even going to get to looking at the options with 3. Yeah, Miles?
Do you think you could use a tree solution to solve the longest sequence in a subarray problem?
Maybe. I don't know. I'd have to look at it. Certainly not on the fly. But I'd have
no,
to.
I'm just curious. I mean, this seems obvious after you explain it, but I think in that instance where you're trying to keep track of not only the sequence but also the sum of the sequence inside of the whole array. Because I was just thinking, I was just working on it yesterday, and it's essentially a double. But it's a nested for loop problem.
I wonder if the greedy approach. I forget. I have to relook at that problem, but I thought that maybe the greedy approach works there. Let me look at it.
It does. Yeah. It does. Yeah. And and there's nothing really to be saved because you still have to know.
Right. The only tricky part with that problem is it's like you also want to make sure there's no. I think that problem has a parameter around no repeats. So like, I guess you use a set, but I think it's not. You're given a set string, right? It's not find all of like it's the longest substring, but it's not like all of the combinations. It's like what's the longest without a repeat showing up, right?
I think I described it wrong. It's the largest sum from a subarray.
Oh, okay.
Like the largest sum of a set of numbers.
Yeah, set of numbers, so a set of integers. Yeah.
And it is fully the greedy approach.
Yeah. Yep. I agree.
One thing I guess one way to start to see this like as a solution is like this is a way of going through all right. Breadth first search is essentially a way of going through all of the options, right? And then the other thing that's why this is useful is it's giving us that hierarchy of we're asking for the shortest path, basically, right? Meaning like the fewest number of levels. So that combination, right, like really makes it this useful. Yeah, go ahead, Miles.
Last one, I promise.
Yeah, sure.
Are there? I've noticed that as we're working with trees more and more, I'm I'm trying to decipher like when is the best time to use a tree oriented solution, or like a greedy approach, I guess is how you would call it, as opposed to, sort of a list or navigating lists. Do you have any tips and tricks? Is this like something we should prefer to try more of the time?
Well, this takes different paths, I guess.
Yeah.
With a list, it doesn't like fan out, right, in the way that
Right.
you can see this does, right? Certainly use a list if you can, but in this case, because it's these different combination, right, depending on how the first one goes, that's changing, the amounts calculated down here. So again, it's one of this like, okay, well, yeah, if it can change based on, whether you're choosing the 1 piece, the 3 piece, or the 4 piece, the only, right, we need, at that point, we kind of need a tree as a way to be exhaustive, right? Explore. So right here, the one way to think of it is, okay, explore all the paths at this, right, with using 1 level. Explore all the paths using 2 levels. Cool. I mean, you'll start to see, like, I wanted to start to show you one of the, right, we can see, like, maybe in a week or so, we'll see another similar kind of problem. But yeah, I think for me, I saw these people are like, oh, use a breadth first search solution. I'm like, what? How do you use a breadth first search solution with a coin change problem? And this is kind of how, right? Is you're not, the children are your different options, right, that you can pursue at each level. So if you didn't understand this through the lecture,